Okay, so we haven't done any homework or anything yet in this class. We just talked about the syllabus and stuff last time. Does anyone have any questions that you've thought of since last time? Yeah.
When you give out assignments, like after class, will you give us paper or is it just gonna be on YouTube?
It's going to be just like this. I'm going to go. Okay, so right here in the announcements, it'll say like for Wednesday 28 units. What would Monday be? The second? Okay, so it'll say something like that. And it'll just be in the announcements there. And so when you see that, what that will mean is go to problems. Let's see, problems for daily assignments. Go to the ones called units and scientific notation and do problems 1 through, I guess there's only 9 of those. So, yep, so that's what it means, sure. And then you'll turn your files in a folder under assignments that I haven't put there yet. Okay. I actually have to think about what numbers it's going to be, but it's going to be something like that. I'll update that later. Any other questions right now?
Yeah, so are those problems like every day?
It's going to be every class. Yeah. So I'll probably do slightly longer assignments on the Wednesday after the Wednesday classes and slightly shorter after the Mondays. Anything else? Okay. So we're going to get into scientific notation and units today. And what I'd recommend is just write down everything I write down. And if you miss anything, the notes are available later, but I think it's a pretty good way to absorb this information. Okay, so every measurement, every scientific measurement has units. In this class, all units are going to be made up of 3 basic unit types. So in this class, all units will be made up of length, so units of length would be like millimeters, feet, meters, miles, and so on. Oh, and by the way, just since we're in a physics class and this comes up sometimes, 1 unit of length that you hear in Star Trek or whatever is light years. I think I'm just mentioning that because a lot of people think that that's a unit of time, but really what it is the distance that light travels in a year. So if you ever hear the term light year, that's talking about a distance, and as you can imagine, it's a very big distance. The second basic unit is time. So units of time are seconds, minutes, hours, days, so on. And the third one is units of mass. And in everyday speech, I think it's sort of common to mix up a little bit to blur the line between units of mass and units of force. For example, pounds is actually a unit of force. It's a, like your weight in pounds is how big a force gravity is applying to you, whereas your mass in kilograms is not how much force gravity is applying to you. It's something else. And we'll talk about what mass is pretty soon. But units of mass, the only two I know of are kilograms and something called slugs. That's the imperial British unit for mass. So this is not, pounds is not included as a unit of mass. And we're going to do pretty much all of our calculations in SI units. So the SI units of these are meters for length, seconds for time, and then kilograms for mass. Okay. There are other basic unit types that we're not going to talk about in this class. The two that come to mind are charge, that has to do with electricity, and the strength of an electric field. Not an electric field, a magnetic field. So basically like an electric related thing and a magnetic related thing. But we're not going to talk about those in this class. You would talk about those if you took Physics 2 after this. So the red is the SI units. SI is just like an international sort of standard unit. You might think that stood for Standard International. It basically does, but it stands for something in French. And I'm not going to try to pronounce it, but it's basically just the international units that are used most often. And so the first thing that we're going to often want to do with units is to convert from one type, one unit to another unit of the same type. Like an easy example would be like, okay, we know that this time interval is going to take 1.5 hours. How many seconds is that? Okay. So now we're going to get into unit conversions. And I'm just going to tell you sort of a general approach, and then we'll do some example problems so you can see this in action. So the first step is there is always a conversion from one unit to another one. So the first step is to find this conversion factor, this thing you're going to multiply by the unwanted unit to get the wanted type of units. So there's always a conversion factor from one unit to another of the same type. And when I say type, I mean like if you're calculating something that has to do with length, you can't convert from meters to seconds. Those aren't the same type. And these unit conversions come from equalities between different units. So for example, 1 mile is equal to 63,360 inches. Okay. And so this gives two possible conversion factors. And these two conversion factors come from the fact that if you divide something by itself, you get 1. And you can always multiply any version of 1 to anything without changing its meaning, you know? So we can think of 1 mile over 63,360 inches as equal to 1. And we can also think of 63,360 inches over 1 mile as equal to 1. Because if you divide something by itself, you get 1. Okay? So we can multiply either one of these times anything we want, and it doesn't change the meaning. Okay? So now we're going to use this by starting with the given quantity. And then we're going to multiply that quantity by the conversion factor that cancels the unwanted units. So we're going to multiply by the conversion factor that cancels the unwanted units. Okay, so let's do this as just an example problem. And let's say that we want to know how many inches there are in 5 miles. Or another way you could say that is convert 5 miles to inches. Well, what we have here are the two possible conversion factors that relate miles to inches. Okay, so we're going to start with 5 miles. That's the given quantity. And now miles are an unwanted unit. We don't want that. We want to end up in inches. Okay, so we're going to multiply by the one of these two ratios that cancels the miles. Okay, and we're going to think of these units the same way we think of algebraic variables. You can think of the meaning of this as 5 times whatever a mile is, just like you can think of it as 5 times x or whatever. And we're going to cancel units the same way we cancel algebraic variables in a fraction. Okay, so if I want to cancel out these miles, one thing about this that I didn't say. As a shorthand, I mean, I'm going to always think of fractions where I'm multiplying values by something with a numerator and a denominator. Instead of writing the parentheses of all the things I'm multiplying, I'm just used to separating them with lines like that. But it just means parentheses. It's just like a shorthand. Okay. Okay, so if we're trying to cancel miles in the numerator of this fraction, do I want the miles of my conversion factor to be in the numerator, like this one, or the denominator, like this one? Denominator, yep. So I'm going to multiply it by 63,360 inches over 1 mile. And you can check to make sure everything cancels the way you want by just going through and canceling any units and seeing what's left. These miles cancel with these miles, just like it would if it was x. And we're left with units of inches. So this is going to work out just like we want. So now all you have to do is multiply and divide out the numbers, and it'll give you the value. and you get 316,800 inches. Any questions about that? Okay, so these three basic unit types, any conversion works the same as the example we just did. But we're also going to see units that are combinations of these, like you're used to miles per hour or meters per second, or, if in chemistry, density is kilograms per meters cubed. So we're also going to have to sometimes do conversions of units that are combinations of these simple types, okay? But it really doesn't change anything. You're just going to do it one by one until all your units are switched over to the new units that you want, okay? So I'm just going to keep doing examples that get kind of increasingly complex. So let's say we want to convert 61 miles per hour, which means miles over hours, to meters per second. And we're going to do that given that there are 1,609.344 meters in a mile. So if any of you ran track in high school, and you call it the mile in high school track, but it's really 1,600 meters. So you're actually running about a little over 9 meters short of a full mile. Okay, so our two possible conversion factors are 1 mile over 1,609.344 meters. And the other possible one is 1,609.344 meters over 1 mile. And we're going to start with our given quantity. So we're going to start with 61. And everything is going to be on a fraction like this. So I'm going to be very clear to myself about what units are in the numerator and what's in the denominator. Okay, so 61 is in the numerator. And then we have miles in the numerator. And then we have hours in the denominator. Okay. And we want to choose the conversion factor that, since these given units are the ones we're trying to cancel, we want to multiply by the one that's going to cancel those. If we did this one here, we'd have meters times miles in the numerator and hours. What would we have? Oh no, that's the one we want. If we did this one, we'd have miles squared over meters times hours. That doesn't cancel the stuff that we don't want. So the one I'm going to use is 1,609.344 meters over 1 mile. I couldn't have said that more confusingly, but do you understand what I'm saying there? So what happens here is, because I chose this one, the miles cancel each other. And the units that we're left with are meters and hours. Okay, well, you could do it in steps like that, but I'm just going to keep going in this same multiplication, because we also don't want the units of time to be hours. We want them to be seconds, okay? And I guess I didn't tell you what we're going to use over here, but we're going to use that 1 hour is equal to 3,600 seconds. So pretend like I wrote that earlier. Like in a problem, you would have to be given both of those. Okay, so the unwanted unit of time that we have here is in the denominator, right? We want to get rid of that hour. So do we want to multiply by something with hours in the numerator or hours in the denominator?
Numerator.
Numerator to cancel the one down here. So I'm going to write the next multiplication factor as 1 hour over 3,600 seconds. And now I'll cancel this and this. And the units we have left are meters in the numerator and seconds in the denominator. And so now we know all we have to do is multiply and divide out the numbers. And if you multiply that out, you get about 27.26 meters per second. Any questions on that one? Um,
27.27 or 26.
I have 2.6, but
Okay.
maybe I rounded carelessly.
Oh, it's okay.
Okay, so the one more new thing that you have to see is the case where you have a unit that's squared or cubed or something like that. So let's say that we want to express 38,640 yards per minute squared in units of meters per second squared. And we want to use that 1 yard is equal to 3 feet. One meter is equal to 3.281 feet. And 1 minute is equal to 60 seconds. So the one thing that's different here is this minutes squared. I'm going to write that as minutes times minutes, okay? And you just have to remember that we have to cancel both of those minutes out and replace them with seconds, okay? So we're going to have to do that one twice. So I'm going to start this with, we have 38,640 yards in the numerator. And then minutes times minutes in the denominator. Okay. And it doesn't matter what order you do this. Multiplication doesn't have a preferred order. I guess I'm going to start by, my first step is going to convert yards to, I'm going to go from yards to feet and then feet to meters. And then when I'm done with that, I'm going to go minutes to seconds. And then when I'm done with that, I'm going to do my other minutes to seconds. And then we'll be done, okay? So to go from yards to feet, I want to have yards in the denominator to cancel this one. So I'll go 3 feet over 1 yard. But now the units of length are in feet. We don't want that, we want meters. So now I want to go, I want to use this second relationship, and I want the feet to be in the denominator. So I'll go 1 meter over 3.281 feet. and those cancel. And now you can see we have length units of meters. So now we can move on to converting the minutes to seconds. So the minutes, let's do this first one here. That's in the denominator. So I want my conversion factor to have it in the numerator so they cancel. So I'll go 1 minute over 60 seconds. So this cancels this. But we still have a unit of minutes here, so we have to do it one more time. So I'll go 1 minute over 60 seconds. And that cancels. And now finally, we have length units of meters, time units of seconds times seconds, or seconds squared. And so now all we have to do is multiply and divide out those numbers, and we'll have the answer. And if you do that, you get something like, well, 9.81 meters per second squared. And this is a quantity we're going to see all the time in this class. Does anyone who's taken physics in high school or anything remember what that is?
Gravity.
Yeah, that's the acceleration of an object that's in free fall on Earth. So if air resistance is negligible, everything falls with that same acceleration as long as it's not being touched by another object. Yes?
With that last step, what were you dividing to get the 9.81?
I was going 38,640 times 3 divided by 3.281, then divided by 60, and then divided by another 60.
Okay.
So yeah, you just have to hit all the numbers in the whole thing.
Yeah.
Any other questions? Okay, let me give you one to try to think through, and feel free to talk to each other about it, talk to the people next to you, walk back there, talk to someone who's not next to you. Ask me questions if you get stuck, but I just want to make sure that you're seeing whether this is registering for you. Okay, so the density of steel, you can mix steel differently, but a pretty good estimate of most alloys, steel alloys, is about 7,000 kilogram per meters cubed. So given that 1 meter is 3.281 feet, what's the density of steel in kilograms per cubic foot? So take a couple minutes and see if you can think through this. Like I said, talk to anybody you want, talk out loud to each other. And then after you've had a couple minutes to work on it, I'll go through. So we're starting with 7,000 kilograms in the numerator. And then I'm going to write it as meters times meters times meters in the denominator. And we're not converting the kilograms, so we can just leave that as it is, but we are converting the meters to feet. So 1 by 1, we just have to do that 3 times. The meters are in the denominator, so the conversion factor we want it in the numerator. So 1 meter over 3.281 feet. Cancels the first one. Do it again. 1 meter over 3.281 feet. There's one left. So 1 meter over 3.281 feet. And the units you have are kilograms over feet, feet, feet. So now we're done. We just have to multiply and divide it out, and you get 198.19 kilograms per cubic foot. Okay, so how many significant figures are there in 7,000? Just one,
Yeah.
right? And how many significant figures are there here? I mean, I have 5 significant figures. So what's going on with that, you might wonder? And the answer is, I don't care about significant figures. So you don't have to worry about that. So, and I don't care about them because I know you take chemistry and chemistry teachers care about it so much that I'm like, I feel free to just do whatever I want. So you can round however you want in this class. I don't care about it. I'm just going to be grading on how you do it. Okay. So yeah, anytime you see something where like, what am I doing with sig figs? It's like, I'm just doing whatever I feel like. I've never even thought about it for a second.
When grading them, do you want to see that specific chart, like that format to solve the problem?
Oh, if you have another way to do conversions, there will be things in this class that I'll want you to do a certain way, but this isn't one of them. So if you're comfortable with unit conversions, scientific notation, any of this first stuff, feel free to keep doing what works for you. I'm just giving you a set of ways that will work if you don't have a preferred way.
And
Any-
you want us to show our work too, right? When we're doing
Yes, I would like you to always show steps. Just like in this case, I don't care how it's formatted, but I want to see all the multiplications that you're doing. Any other questions? Okay, so the next thing I want to talk about is scientific notation. And the idea of scientific notation is that any number can be expressed as plus or minus, and then 1 non-zero unit, and then a decimal point, and then whatever the decimal is, times 10 to some integer. Okay, so like for example, what I mean is negative 3,481.9 is equal to negative 3.4819 times 10 to the positive third power. Okay, so you have the sign stays the same. The decimal is in a place where you only have one non-zero digit before the decimal, and then you have an integer as the exponent. And you can also do numbers with absolute values less than 1 that way. So 0.0087 is equal to 8.7 times 10 to the minus third. So any number that's absolute value is less than 1 is going to have a negative exponent, and any number whose absolute value is bigger than 1 is going to have a positive exponent. So that's the first sanity check. You know, if that doesn't happen, then something went wrong. In order to do this, well, let me write that down actually. So if the absolute value is greater than 1, then the exponent is positive. And if the absolute value is less than 1, then the exponent is negative. Okay, so in order to work with scientific notation, you need 2 skills, basically. You need to be able to go from a standard number to scientific notation, and you need to be able to go from scientific notation to a standard number. And if you're comfortable with this, and I'm sure there's a lot of people who are just pretty comfortable thinking this through, I can't say that I use these steps when I do it, but I'm going to give you a set of steps that work if you'd like an approach to this, okay? But if you don't like this approach, feel free to ignore it and do it your way. And some of you have calculators that'll just do this for you, and I'm not even going to be mad about that. Like, great, you got a good calculator. You know, I'm going to assume that you'll have that with you when you need it. So feel free to use your calculators, but if you need an approach to doing this, this will do it. Okay, so the first one is given a number in standard notation, express it in scientific notation. And I'm going to do this sort of as I go. I'm going to show these steps with the number negative 541.6. Okay, so the first step, A, is count the number of places and that number is going to be called capital N, that you have to move the decimal point left or right so that you get one leading digit, one non-zero digit before the decimal point. Okay, so for this one, I have to move that decimal point 2 places to the left. And then the second step is if you moved to the left, then you're going to be multiplying by times 10 to the power of positive n. And if you had to move the decimal point to the right, then it's times 10 to the negative n. Okay, so for the one I did, I moved it 2 to the left. So the answer is going to be negative 5.416 times 10 to the positive n, or positive 2. The second thing you have to be able to do is go from scientific notation to standard notation. And I'll do this with the number, so I'll start with 6.52 times 10 to the minus fourth. So the first step is the absolute value of the exponent is, we're going to call that n. So in the case of this example, n is equal to 4. And now if the exponent is positive, my computer needs a little break sometimes. Okay, so if the exponent is positive, then move the decimal point 'n' places, whatever the n is, n places to the right. And if the exponent is negative, then move the decimal point n places to the left. One thing I want you to notice, let me finish the example. So in our case, it was negative. So we're going to move our decimal point 4 places to the left. So we have 6, 5, 2. And we're going to move it 4 places to the left. So that's 1, 2, 3, 4. You can think of like zeros going on forever in both directions. And so our answer is going to be 0.000652. Okay. I want you to notice that these two, like whether you're going from standard notation to scientific notation or the other way, positive and negative are associated with different directions, the opposite directions for those two. And it kind of makes sense. It's like whether you're moving the decimal point to the spot with one leading digit, or whether you're moving the decimal point from the one leading digit back to the original spot. You know, you're always going one way for one of them and the other way for the other. Are you with me on that? One cool thing about scientific notation is, so remember doing significant figures, there are all these like kind of abstract feeling rules about when digits count as significant figures. And you kind of have to think like, okay, well, so like with this 7,000, you know, like, where did I, here. I said that as one significant figure. Well, you learned maybe you didn't, I don't know. When I was a boy, we learned, like they taught it to us in this whole list of rules. And it's like, okay, if the zeros are to the right of the number and there's no decimal after it, then none of those zeros count as significant figures. But if they are decimals, then they all count as significant figures, you know? With scientific notation, if you get your numbers in scientific notation, it's so easy. Every digit before the times 10 part is significant, and that's just the end of it. So, so where are my examples? So this one has well, it does, but this one has 4 significant figures because you look at it in scientific notation, there's 4 digits before the times 10 to the whatever, and that's the end of it. Yep.
And should it always be 4 significant figures too if we're doing it in scientific notation?
No, that's just what I gave you. So that just depends on the problem.
Oh, yeah, you're right, because some of them don't.
This one only has 3.
Yeah.
And it might, you know, if you forget the rules, it might not be clear that it has 3 from this, but from the scientific notation, it's perfectly clear. 1, 2, 3, and you're done. Okay.
And that'll have the same amount of sig figs as, that number will have the same amount of sig figs as it being in scientific notation or standard notation.
Right.
Too, right?
Yep, that's right. Any questions about that? So yeah, you just, if you want to, we're not going to use that in this class because I don't care about significant figures, but if you just skip the times 10 to the whatever part and you have it written in scientific notation, every digit is significant. Okay, so when is scientific notation helpful? Yeah.
When you have like a really long number with a lot of zeros or something.
Yeah, that's right. Usually, right, very big numbers or very small numbers. This is such a nice way to write it. And in physics, we have both of those, you know. You do physics with forces and masses of planets and stuff. Those are very, very big. And you also do masses and charges of electrons and things, and that's very, very small. And so, like, for example, in kilograms, the mass of the Earth is something like 6 times 10 to the 24th power. So if you were going to write that number out in standard notation, you'd have to be really careful to write out, you know, 23 zeros. And if you mess up and miss one, you're not off by a little, you're off by 10 times, you know. And so this is just a really useful thing for really big and really small numbers. Okay, the last part of this units stuff that I need to tell you is unit prefixes. So I'm going to give you just the ones that we're going to see. There are others too, but I'm going to go from smallest to biggest. So micro is denoted with the Greek letter mu that looks kind of like a scripty in between a scripty M and a scripty U, which kind of makes sense for this one because that's how you spell it, MU. And the meaning of micro is times 10 to the minus 6. Yes.
So in the past, I've seen scientific notation being denoted with the capital E instead of times 10 to the blank. Is that
Oh, yeah. That's fine with me. I think people started doing that because that's how you enter it into a calculator usually. And actually, I teach classes where I write it that way too. In this class, I tend not to, but it's fine with me. What I just don't want is people to. Sometimes people make this mistake of saying like 5 times e to the sixth. And that also has a meaning, and it's not the same meaning, you know. But so you can either write it as 5 times 10 to the 6 or as 5 capital E 6. Either one of those is fine with me. Okay, so micro means times 10 to the minus 6. Milli with a lowercase m means times 10 to the minus third. Centi, lowercase c, means times 10 to the minus 2. Kilo is a lowercase k, and that means times 10 to the positive 3. And mega is a capital M, and that means times 10 to the positive 6. And we want to be able to do two things with these prefixes. We want to be able to go from something with using one of these prefixes to using no prefix. And then we want to be able to go from something using no prefix to something using a prefix. And then you can do anything you want to go from a prefix to a different prefix. You just have to take that intermediate step of going to no prefix in the middle, if you know what I mean. So okay, we just need these two steps. One of them is kind of immediate, and one of them takes sort of one step of math. So the first way you can go is from something with a prefix to something with no prefix. And this is the easiest one. This is immediate. All you do there is just replace the prefix with the mathematical meaning I gave you. So just replace the prefix with the mathematical meaning. So for example, let's say we wanted to go from 50 kilometers to expressing that in meters. So I'm just going to replace the K, the kilo prefix, with times 10 to the third. And then just put it in standard or scientific notation and you're done. So this is like 5 times 10 to the fourth meters. So all I did was just kind of use the definition of it. To go the other way, you're going to do it sort of like a unit conversion. So if you're starting with no prefix and going to a prefix, you're going to do it like a unit conversion. Where the conversion factor uses the prefix definition. Okay, so for example, let's say that I want to go from 100 grams and I want to express that in micrograms. Or mu g. Okay, well, we know that 1 microgram, using the definition of micro, is equal to 1 times 10 to the minus 6 grams. Right, I just replaced that micro with its definition. And now I can make this into either one of the conversion factors. So we want to start with this quantity 100 grams. My conversion factor that I want has grams in the denominator, so it cancels this. So I'll go 1 microgram over 1 times 10 to the minus 6 grams. And now those cancel. And we get 1 times 10 to the positive 4th micrograms. Yep.
Is the 100 grams just going to be over 1, right?
Yeah, that's right. Yeah, you could write the 1 down here if you want. Any other questions about that? Okay, let's do an example. I'm going to have you go through the steps. So let's say that what we want is, okay, so here's the question. How many microseconds in a millisecond? Yes?
That math at the top there seems a bit off.
The one right above?
That'd be 100 divided by 1 times 10 to the negative 6, which would give a bigger number than just 1 times 10 to the 4.
Oh, I did go the wrong direction. You're right. Thank you. I guess I made that mistake in my notes. Thank you. So the way this works. Oh. This is like 1 times 10 to the 2 divided by 1 times 10 to the minus 6, which is the same thing as 1 times 10 to the 6. And that is 1 times 10 to the 8. Thank you. Everyone with me on that? Do you guys remember those exponent rules at all? We won't have to do too much of that kind of stuff, but if you have the same base So let's say the A's are the same here, and they have different exponents, and you're multiplying them together. This is equal to A to the power of M plus N. And if you have A to the M over A to the N, that's equal to A to the power of M minus N. So sometimes that stuff is helpful with scientific notation. Okay, so what we're going to do to convert, so we're starting with milliseconds, and we want to convert to microseconds. You know, another way to say this is convert 1 millisecond to microseconds. So what we're going to do is convert 1 millisecond to seconds, and then we're going to convert 1 second to 1 microsecond. So take a couple minutes and do that first step. So we're going to go from 1 millisecond to seconds. And so we're going to start with 1 millisecond, and we're just going to replace the milli with times 10 to the minus third. And so there we go. Okay, I just replaced the M with the stuff in parentheses. And now the next step is we want to go from 1 times 10 to the minus third seconds to microseconds. Okay, so this time we're going to think about a conversion factor using that 1 microsecond is equal to 1 times 10 to the minus 6 seconds. And we're going to start with 1 times 10 to the minus third seconds. We're going to use the conversion factor that cancels seconds. So we want 1 times 10 to the minus 6 seconds down there. 1 microsecond on top. The seconds cancel. And we get 1 times 10 to the third microseconds. Anybody have any questions about that? Okay, well, that's it for today. By tonight, I will put up an assignment for you that'll be due on Monday. And I'm done with half of you for the week, and then the other half have lab at 1:30, right next door. Although I do have office hours if anybody has any questions or wants to talk about anything.
Are we gonna get the results of that test you just took in the lab?
Yeah, I can get that to you. I haven't graded it yet.